Hello everyone, here is our design for hopper, pneumatic, transport and fluidization for fluid cracking catalyst.
First, we'll proceed to the design of hopper. Hoppers are used in the industry for protection and storage of powdered materials, in which it is usually designed such that they are easy to load and unload. It is greatly affected by the rate of flow of the powder out of the hopper, how much the stored material can discharge, and whether the mixing of solid sizes that reduces the effective holding capacity of the hopper. There are two types of flow in the hopper, which are the mass flow and the core flow. As can be seen in the video on top, is an example of the mass flow when all the powder in a silo is in a motion whenever any of it is thrown from the outlet. The motion is said to be uniform and steady state to be closely proximate. Meanwhile, the video below shows an example of core flow. In core flow, all the powder flows towards the outlet of the silo in a channel formed within the powder itself. As can be seen, the regions of powder lower down in the hopper are stagnant until the hopper is almost empty. In determining the critical condition for flow, sigma y is plotted against sigma c. A plot of flow factor Ff and powder flow function showing the intersect point defining the flow or no flow transition. The intersection point denotes the sigma critical. When the actual stress developed is more than sigma critical, it means there are no flows occurs. And when the actual stress developed is less than the sigma critical, it means there are flow occurs. For example, the design of hopper was being done for 10,000 kg production of fluid catalytic retin powder FCC. The first step is to determine pairs of value of unconfined wheel stress and compacting stress, the value of the effective angle of internal friction, and the angle of wall friction. There are three values of data obtained from the Morse circle. These values are being used in producing the powder flow function PFF. From the data obtained by the journal, value of delta obtained from shear cell test is 30 degree with kinematic wall friction of 23 degree. In step 2, the value of hopper flow factor and semi-included angle of conical hopper wall slope is obtained. It is given that the wall friction angle equals to 23 degree. The bulk density is 868 kg per meter cube, angle of internal friction of 30 degree. Thus, by using hopper flow factor values for conical channels 30 degree and kinematic wall friction of 20 degree, the hopper flow factor will be 1.8. Next, in constructing the limiting condition, powder flow function and hopper flow factor are combined to give the stress combining to the critical flow and no flow condition sigma critical. This will give sigma y is equals to 0.556 sigma c. Both powder flow function PFF and limiting condition were plotted to obtain value of sigma critical. From the graph plotted, the sigma critical is equals to 1.006 kN. By substituting all the value in the equation of 10.4 and 10.5 of particular technology book by Martin Rhodes, value of conical outlet of 2.333 and minimum size of hopper outlet of 0.2756 meter were obtained. The last step is in determining the size of a silo. Rearranging equation of M equals to rho V, this will give the volume of the silo, which equals to 11.5207 meter cube. Using heuristic, the diameter of the silo is 1.564 meter. Finally, the height of the hopper and silo can be determined, which gives a value of 1.8786 meter with an outlet mass flow rate of 314.3654 kg per second. In conclusion, the design of hopper has completed. For production of 10,000 kg of FCC powder with height of 1.8786 meter and diameter of 1.564 meter. Second, we'll continue with the design of pneumatic transport. What is pneumatic transport? Pneumatic transport is a way of transporting particulate by using gas as a medium with an add of pipelines. There are two types of pneumatic transport. First is the dilute phase pneumatic transport. Second is the dense phase pneumatic transport. Upon designing pneumatic transport, there are three things that need to be focused on. First is the total pressure drop in the pipeline. Second are bands, equipment, and pipe. Third are velocities, which include superficial gas velocity, solid velocity, and slip velocity. So this is the schematic design of dilute pneumatic transport for slip cracking catalyst FCC. The pneumatic transport will transport the particles from the storage hopper to the fluidized bed. The pneumatic transport will include the horizontal sections and the vertical sections together with the beds. So this is the problem statement for the design, where we are required to design a dilute phase pneumatic transport system, which is used to transport 314.2654 kg per second of fluid cracking catalyst FCC. The particle density of fluid cracking catalyst FCC is 1477 kg per meter cube, with particle size of 64 micrometer. In the pneumatic transport design, we include the vertical distance of 15.24 meter and horizontal distance of 30.48 meter by using ambient air. There are two bands required in this design. The first step is the selection of pipe size. The pipe size chosen for this design is 219.1 mm based on the ASTM standard. It was selected because it has the nearest size to the hopper outlet diameter. Step is the determination of gas velocity. In order to calculate the gas velocity, we first need to determine the sortation velocity. Sortation velocity can be calculated by using risk correlation equation. From the risk correlation equation, the sortation velocity obtained is 58.6206 meter per second. The sortation velocity was then times with 1.5, which is the safety margin in consideration to the accuracy of the correlation. Therefore, the superficial gas velocity obtained is 87.9309 meter per second. The third step is to calculate the pressure loss in the horizontal section. By using the following equation, the pressure loss in horizontal sections are calculated. There are 6 components to be considered in calculating the pressure loss for horizontal and vertical flow. These are the details on the following equation. Based on the horizontal sections design, term 1 and term 2 is necessary for this calculation. As for term 3, it will be calculated by using the fanning friction equation, where pressure loss due to gas-to-wall friction is independent of the presence of solids. Term 4 will be calculated using Hinkle correlation. As for terms 5 and 6, it was assumed that theta is equals to 0. Therefore, we need to find the particle velocity, voidage, and gas velocity. The particle velocity can be calculated by using the following equation. From the following equation, we obtain the particle velocity of 76.0320 meter per second. Voidage was calculated by using continuity equation, where the voidage obtained is 0.9257. Then the gas velocity was calculated, which is at 2.1346 meter per second. Step 2 is to find the Reynolds particle, drag coefficient, solid friction factor, and gas friction factor. The value for Reynolds particle obtained is 26.0024. From the Reynolds particle, we can calculate the drag coefficient, which is 2.6192. Then, we can calculate the solid friction factor and gas friction factor. When all the values are obtained, the pressure loss in horizontal sections can be calculated. The pressure loss in the horizontal section is 3504,357.635 Pascal. Step 4 is to calculate the pressure loss in vertical section. The equation used to calculate the pressure loss in vertical section is similar to the equation used to calculate the pressure loss in horizontal section. Only term 4 will be calculated differently, which is by using Cono and Saito correlation. Unlike horizontal section, vertical section design assumes 0 for term 1 and term 2 since the initial acceleration of solid and gas takes place in horizontal section. As for term 3, it will be calculated by using the fanning friction equation where solid has negligible effect on the pressure loss. Term 4 will be calculated using modified Cono and Saito correlation. As for terms 5 and 6, it was assumed that theta is equals to 90 degrees. To calculate the vertical section pressure loss, we need to find the voidage, which is by combining the continuity equation and equation solid velocity for vertical section. By combining those two equations, we will obtain a quadratic equation. However, to solve the quadratic equation, we need to know the single particle terminal velocity, which can be estimated by using the following equation to obtain the value of 18.31. So from the figure, we can actually obtain the value of Reynolds terminal, which is assumed to be 2.8. From the Reynolds terminal, we can rearrange the equation to find the terminal velocity, which is 0.6571 meter per second. By solving the quadratic equation, we can obtain the voidage, which is 0.9393. Then, we can finally calculate the vertical section pressure loss, which is 52610.1867 Pascal. The fifth step is to calculate the pressure loss across band. Here, two 90-degree bands are used. The pressure loss across each 90-degree band is taken to be equivalent to 7.5 of vertical pipe. Therefore, we need to find the pressure loss per meter of vertical pipe, which is 3452.1120 Pascal per meter. Thus, the pressure drop across two 90-degree bands is equal to 52610.1867 Pascal. The sixth step is to calculate the total pressure loss, which is by combining the loss at horizontal sections, loss at vertical section, and loss at bend. The total pressure loss is 36.0958 bar. The last step is to compare the calculated and allowable pressure loss. The pressure loss calculated will be compared to the allowable pressure loss of the system, which depend on the blower used for that particular system. For this case, the pressure loss of the system is quite high. Therefore, it requires a blower that can withstand such pressure loss.
Okay, next we proceed to the next part, which is the fluidized bed. A fluidized bed is a packed bed which the fluid flow through it with a high velocity, that the bed is loosened and the particle fluid mixture behaves like a fluid. Okay, it provides a uniform contact for the solid and the fluid itself. The application of fluidized bed is for drying, cooling, and coating of solid. Next we proceed to the fluidized bed design. Okay. First we obtain the minimum fluidization velocity, which is 0.00154 meter per second, and the minimum bubble velocity, which is 0.0045 meter per second. Both data we obtain from the journal. Next, we use air as the fluid. The density of air is 1.225 kilogram per meter cube, and the air viscosity is 1.983 exponent negative 5 kilogram per meter dot second. Next, we calculate the superficial velocity, the U0, using these two equations. We calculate the equation simultaneously to get the U0, which is 0.00242 meter per second. The value of the superficial velocity is very low, which is below 1 meter per second. Therefore, there is no bubble form, and the flow regime is at the particulate region, and the value of UMF, U0 and UMB is follow the U range for the particulate regime. To find the dimension of the fluidized bed, first we calculate the volume of the bed, which we can calculate using bulk density and the mass. The value that we get is 11.52 cubic meter. Okay. Next, to find the dimension, we assume that the diameter of the bed is 2 meter. From the value of the bed, we get the height of the bed, which is 3.67 meter. For the height of the vessel, we increase a little bit from the height of the bed, which we use the value of 4 meter.